Hello there, and welcome to Drift to the Stars. I'm so glad you found your way here tonight. Before we begin, I'd love to know, what country are you writing from, and what time is it there right now? Are you listening to this alone, perhaps settling in for a quiet night of sleep while your mind drifts toward the deep blue edges of our solar system? Or are you gathered around a table with family, the sounds of an evening meal still warm in the air around you? Tonight we are traveling to the farthest planet, a world of impossible winds, dark storms, and a blue so deep it looks like something dreamed rather than discovered. If tonight's journey brings you something peaceful, something worth carrying into sleep or sharing over a meal, I'd be so grateful if you passed it along. A like or a share helps other people find their way here too. Now if you're ready, let's begin. There is a planet at the edge of our solar system that no human eye has ever found on its own. Not because it is too strange or too small or somehow hiding, but because the light reaching it from the sun arrives so thinned by distance that even a sky, perfectly dark, perfectly still, cannot deliver it to unaided eyes. It has always been there, quietly, steadily turning. And for most of human history, no one knew. Neptune was not discovered by looking. It was discovered by thinking. In the mid-1800s, astronomers noticed that Uranus was not moving quite the way it should. Something was pulling at it gently, invisibly, from far away. Two mathematicians working independently in different countries sat down with the known laws of gravity and calculated where that something had to be. They pointed, others looked, and there it was, exactly where the numbers said it would be. A whole world found first in an equation. That has always felt like one of the quieter miracles of science, that the universe follows rules patient enough to be written down and generous enough to reveal what we haven't seen yet. And yet, even knowing it is there, you still cannot find it tonight. Step outside on the clearest evening imaginable. Let your eyes adjust until the Milky Way spreads across the sky like something spilled. Neptune will not appear. It sits just beyond the threshold of what the human eye can gather, its reflected sunlight arriving too faintly to register as anything but darkness. It is not invisible, it is simply beyond reach. There is something quietly humbling in that. We live on a planet where our senses evolved to handle a very specific range of scales: the deer in the field, the storm on the horizon, the face across the fire. The solar system extends far past all of that. Neptune exists in a register our bodies were never built to feel directly. And yet we know it is there. We know its color, its winds, its moons, its storms. We know things about it that we cannot see because we built tools that extended our reach far beyond our eyes. That gap between what we sense and what we know is where so much of science quietly lives. Unhurried, patient, working at the edge of what is possible. One orbit around the Sunday. For Earth, that takes 1 year, 4 seasons, 12 months, the long, slow turn from winter back to winter. Neptune's orbit is the same journey, the same ellipse, the same destination, but the path is so much longer, and Neptune moves with such patience that a single orbit takes 165 Earth years. A person born today would need to live to be 165 to watch Neptune complete just one lap. Neptune was discovered in 1846. The first full year of its orbit, observed by human eyes, only ended in 2011. People who had spent entire careers studying this planet never saw it complete even a fraction of one full trip around the Sunday. There is something worth sitting with in that. The timescales Neptune operates on are so far beyond a human life that the planet barely registers our presence at all. While civilizations rose, while languages were born and forgotten, while the borders of every nation on Earth were drawn and redrawn, Neptune was simply moving, slowly, steadily tracing its enormous circle. The universe keeps its own rhythms, and they are not ours. And yet within all that vastness and slowness there is a kind of speed. Neptune's day is short. While the planet takes 165 years to make one journey around the Sun, it completes a full rotation on its own axis in just about 16 hours. The planet is simultaneously one of the slowest travelers and one of the quickest spinners in the outer solar system. Think of it as the difference between a long walk and a spinning top. The walk takes a lifetime. The spin is over before a good night's sleep. This rapid rotation shapes everything about Neptune's appearance, the way its clouds band into wide stripes, the way its storms form and wheel and drift. A planet spinning that quickly is constantly in motion at its surface, its atmosphere stirred into patterns that shift from one day to the next. 16 hours is not much time. It is roughly the length of a long, full day for a person waking, working, thinking, eating, moving through the world, and arriving at evening again. Neptune completes that same arc, that same rotation from one face toward the sun and back into shadow, in roughly the time it takes to live one waking life. There is something almost companionable in that. Now consider the wind. Neptune is the windiest planet in the solar system. Not Mars, where dust storms turn the sky amber. Not Jupiter, where the great red spot has churned for centuries. Neptune, the farthest planet, the one that receives the least sunlight, the one moving slowly through the cold outer dark. Its winds can reach 2,100 kilometers per hour. To make that feel real, the fastest winds ever recorded on Earth's surface reached around 400 kilometers per hour during a tropical cyclone, and that was considered catastrophic. Neptune's winds move more than 5 times faster than that, and they do it not as an exception, not as a storm, but as a baseline condition of the atmosphere. Scientists have not fully agreed on why. Neptune receives so little energy from the sun that the winds should, by most models, be calmer. Yet they are not. Something within the planet itself, some internal heat source, some dynamic in the deep atmosphere, appears to be driving circulation far beyond what sunlight alone would allow. The universe does not always match our models. Sometimes it simply does what it does and leaves us to catch up. Even as you rest, right now, your breath moves in and out at a pace measured in seconds. Gentle, unhurried, barely audible in the quiet of wherever you are. Neptune's upper atmosphere moves at speeds so far beyond that it becomes difficult to hold the two images side by side. And yet both are real. Both are happening right now at this moment, your slow breath and Neptune's howling upper winds, both part of the same solar system, both made of atoms that have been cycling through the universe for billions of years. The contrast is not there to make you feel small. It is there to show you how wide the range of things truly is, and that you are somewhere inside that range, breathing quietly, which is its own kind of fact worth noticing. Stillness has a place in a universe this large. Yours is one of them. Neptune generates more heat than it receives. Hold that for a moment. The planet sits so far from the sun that sunlight arrives barely strong enough to be measured at its surface. And yet Neptune radiates significantly more energy outward into space than it ever takes in from that distant star. The planet has an internal heat source, something deep inside, still releasing warmth that was stored during formation billions of years ago, when Neptune was young and still collapsing from the swirling cloud of gas and dust that became the solar system. That warmth has been slowly leaking out ever since. It is the heat of becoming, the energy of a world still in some quiet way settling into itself. And it matters enormously for Neptune's atmosphere. That internal warmth drives convection, stirs the clouds, feeds the winds, keeps the planet far more active than its sunlit energy alone could explain. It is, in a way, Neptune still carrying something from its beginning, a warmth held over from a time before it was recognizable as a world. Some things are shaped by where they came from, long after the origin is gone. Sunlight reaches Earth in about 8 minutes. Standing in the afternoon sun, the warmth on your face was light that left the sun 8 minutes before it arrived. It is a short enough trip to imagine a beam of light crossing the solar system, arriving at your skin still moving at full speed. At Neptune's distance, that same journey takes over 4 hours. By the time sunlight reaches Neptune, it has crossed a space so immense that it arrives 248 times fainter than it does at Earth. Not dimmer, in a gentle, gradual way. Dramatically, measurably, vastly fainter. Noon on Neptune would look darker than a deeply overcast evening here. And yet the sun is still the sun from there, still visible, still the gravitational anchor holding Neptune in its vast orbit. still technically illuminating the planet's blue face just so faintly that the word light almost needs a different meaning. Distance changes everything it touches. Not the thing itself, only the experience of it. The sun shines just as brightly. Neptune simply stands very, very far away. There was once a storm on Neptune the size of Earth. Not a small disturbance. Not a ripple in the cloud layer. A dark oval absence in the blue atmosphere, wide enough to swallow our entire planet whole, spinning with the slow authority of something that had been there a very long time. Astronomers called it the Great Dark Spot, and when Voyager 2 passed Neptune in 1989, it was one of the first things they noticed, a vast shadow turning in the southern hemisphere, patient and enormous. Then, 5 years later, they looked again. It was gone. The Hubble Space Telescope searched the place where the Great Dark Spot had been and found only smooth blue atmosphere undisturbed, as though the storm had simply decided to stop. A new dark spot appeared in the northern hemisphere not long after, which also eventually faded. Neptune's storms do not seem to last the way Jupiter's do. They come, they turn, they dissolve back into the atmosphere they emerged from, leaving no visible scar. There is something quietly remarkable about impermanence at that scale. A storm the size of a world, and still temporary, still subject to change. Even the largest things eventually settle, descend far enough into Neptune, past the clouds and the methane haze, and the roaring wind layers, and the temperature begins to climb. Not gently, dramatically. Deep inside, Neptune pressures build to levels that compress matter into states that have no everyday equivalent, and the temperatures in that interior may reach somewhere around 5,000 degrees Celsius, comparable to the surface of the Sun, which sits at around 5,500 degrees Celsius. These two numbers arrive side by side, like a quiet impossibility. The surface of our nearest star and the deep interior of the farthest planet, reaching nearly the same heat through completely different paths. One is driven by nuclear fusion, the engine of stars. The other is the lingering warmth of formation of gravitational compression of a world that has been slowly releasing its birth heat for billions of years. The sun burns. Neptune simply remembers. And what that interior heat does to the material pressing in around it is extraordinary in ways we are only beginning to understand. The deeper you go, the stranger the physics becomes, until the planet stops resembling anything in ordinary experience and becomes something else entirely. Strange and ancient and still. Neptune has 16 known moons. They range from Triton, large enough to hold a thin atmosphere and active geology, all the way down to small irregular bodies barely wider than a city tumbling in distant orbits that suggest they were captured rather than born in place. Each one is a different story. Each one arrived at its current path through its own particular history of gravity and collision and time. 16 worlds orbiting one blue planet. Some of them have never been seen up close. Some of them are known only by their orbital path, their position calculated across years of careful observation, their shape and surface entirely unknown. They exist in the record as points of light, as numbers in an equation, as places that have names but no faces yet. There is something worth holding in, that the idea that named things can still be almost entirely unknown, that giving something a name is just the very first step toward understanding it, and that understanding itself may take generations still to come. 16 moons patient in their orbits, waiting to be properly seen. Even as you rest right now, the atoms in your body, carbon, oxygen, nitrogen, iron, were forged inside stars that lived and died long before our solar system existed. Those atoms drifted through space as gas and dust slowly drawn together by gravity, eventually becoming the cloud that collapsed into the sun, the planets, and everything on them. The same cloud that became Neptune also became you. Not as a metaphor, as chemistry, as physics, as the actual documented history of the matter you are made of. You and Neptune share an origin. Not a distant poetic one, but a real molecular one, the same reservoir, the same ancient swirling cloud separated into different forms by the same forces, acting on the same raw material. That origin is not behind you somewhere in the past. It is present in every atom you carry. It is the ground of your existence in the most literal sense. You are, in some quiet and genuine way, made of the same beginning. Triton does something no other large moon in the solar system does. It orbits backward. Every major moon of every other planet orbits in the same direction the planet spins, the natural result of forming from the same rotating disk of material that made the planet itself. Triton does not. It circles Neptune in the opposite direction, moving against the grain of the entire system on a path tilted steeply relative to Neptune's equator. This is considered strong evidence that Triton was not born in orbit around Neptune. It was captured. It arrived from somewhere else, most likely from the Kuiper Belt, the vast region of icy objects beyond Neptune's orbit, and was pulled in by Neptune's gravity long after the planet had already formed. The capture itself would have been an event of extraordinary violence. The kind of gravitational interaction required to slow an incoming object enough to trap it in orbit releases energy equivalent to catastrophic collisions and massive disruptions of whatever moons may have existed there before. And now Triton drifts in its backward orbit, calm and quiet as though it had always been there. Some arrivals leave very little evidence of how difficult they were. That backward orbit comes at a cost. Because Triton moves against the direction of Neptune's rotation, the planet's gravity is very slowly, very patiently, pulling energy out of Triton's orbit. The moon is spiraling inward, not quickly, not in any way that would register across a human lifetime or even many human generations, but measurably, verifiably, on a trajectory that ends in dissolution. In roughly 3.6 billion years, Triton will pass within a distance of Neptune called the Roche, limit the point at which a moon's own gravity can no longer hold it together against the tidal forces of the planet it orbits. At that point, Triton will break apart. Its material will spread into a ring system around Neptune, wide and diffuse, more spectacular than the faint rings that exist there now. Neptune will one day be a ringed planet, and Triton, ancient captured traveling backward, will have become the material of that ring, a world transformed into an orbit. The patience required to hold that thought, to sit with a timeline that long, is its own kind of practice. Some endings take longer than stars. Triton has geysers. On a moon where the surface temperature drops to around -235 degrees Celsius, one of the coldest surfaces ever measured in the solar system, something is erupting. Dark plumes of nitrogen gas shoot upward several kilometers from the surface, carried by winds in Triton's thin atmosphere, before dispersing into dark streaks across the frozen terrain. These geysers are not driven by internal volcanic heat the way geysers on Earth are. They are driven by sunlight. Triton's surface is coated in nitrogen ice, and where the sun's rays, faint as they are, at Neptune's distance, penetrate that transparent ice and warm the darker material beneath the nitrogen, vaporizes rapidly. The pressure builds until it punches through the ice above and erupts. Sunlight so faint it would barely cast a shadow on Earth is enough to puncture a frozen moon. The geysers leave dark streaks across Triton's pale pink surface, pointing in the direction the winds carried them when they erupted. A record of past eruptions written in nitrogen and shadow, visible from orbit. A cold, quiet moon marked by its own breath. Neptune is blue. Not as a label or a convention. It is genuinely, visibly, photographically blue. The color arrives through a specific physical process. Methane, in Neptune's upper atmosphere, absorbs red wavelengths of sunlight and reflects blue ones back into space. The result is a color so deep and saturated that early images of Neptune were sometimes mistaken for artistic renderings. But there is something slightly puzzling inside that straightforward explanation. Uranus has methane in its atmosphere too, in similar concentrations. And Uranus is also blue, but a paler, hazier, almost washed-out blue-green, noticeably different from Neptune's rich, deep color. The methane content alone does not fully explain the difference. Something about the structure of Neptune's atmosphere, perhaps the way its clouds are layered, or the way its internal heat drives circulation, produces a color that Uranus, despite its similar chemistry, does not quite match. Scientists are still working toward a full explanation. And so Neptune's blue remains, for now, not entirely explained. A color at the edge of the solar system, absorbing the red parts of faint sunlight and returning something unexpectedly beautiful. The universe does not always explain its aesthetic choices. Neptune's blue is not quite fixed. It shifts. Slowly, over years and decades, the shade of the planet's atmosphere changes in ways that careful observation has begun to document. During Neptune's long southern summer, which has been unfolding since 2005, the planet's color has shown measurable variation, subtle brightening in some regions, deepening in others, as seasonal changes in the upper atmosphere alter which wavelengths reach the instruments pointed at it from Earth. A planet's color changing with its seasons is not in itself surprising, but Neptune's seasons last more than 40 Earth years each. The color shifts happening now are part of a cycle so slow that no single astronomer will observe more than a fraction of it across an entire career. And the full reasons behind those shifts are still being worked out. The relationship between Neptune's internal heat, its atmospheric chemistry, its distance from the Sun, and its color is more tangled than the simple methane story suggests. Scientists are still listening carefully to what the blue is saying. Some questions are not answered in a single lifetime. Some are answered slowly across generations of patient-looking each observer, adding one small piece to something they will never see completed. That kind of work requires a particular kind of love for the question itself. Neptune's rings are not what most people picture when they imagine a ringed planet. They are faint, dark, incomplete in places, broken into arcs rather than full circles made of materials so dim that they were not confirmed to exist until Voyager 2 passed through the system in 1989. Even then, they required careful analysis to distinguish from the surrounding darkness. Saturn's rings are made largely of bright water ice, reflecting sunlight in a way that makes them visible even through a modest backyard telescope. Neptune's rings are made of something else, entirely dark, organic material, carbon-rich compounds that absorb light rather than reflect it. They are, in a sense, rings made of shadow. The difference is not just aesthetic. It tells a story about where the material came from, how long it has been there, how radiation and time have processed it into something darker than it may once have been. Looking at Neptune's rings is like looking at something that has been slowly changed by everything that touched it. Quietly, over an enormous span of time, the rings became what they are. Those rings are not complete circles. Neptune's outermost ring, named Adams after the mathematician John Couch Adams, who helped predict the planet's location, has distinct clumps within it, regions where the material bunches together into arcs rather than spreading evenly around the orbit. These arcs have names: liberty, equality, fraternity, courage. They were discovered before the full ring was confirmed, which briefly led astronomers to wonder whether Neptune had arcs instead of rings at all. Why the material clumps the way it does, rather than spreading evenly the way physics might suggest, is still a subject of genuine scientific debate. One leading explanation involves gravitational resonance with a nearby moon called Galatea, whose gravity may be herding the ring particles into those concentrated regions, keeping them bunched rather than dispersed. But the details are not fully settled, and so the arcs persist, named, observed, partially explained, still holding their shape in the dark beyond the planet patient, as everything else in Neptune's system seems to be. Some structures hold together for reasons we are still learning to read. Inside Neptune, carbon may be doing something extraordinary. At the pressures and temperatures that exist deep within the planet, pressures millions of times greater than anything at Earth's surface, temperatures hotter than most things we encounter in daily life, carbon atoms may be compressed so tightly that they form diamonds, not traces, not occasional crystals, potentially vast quantities of diamond, forming continuously in the interior and then sinking slowly toward the core under their own weight. This is not science fiction. It is a hypothesis supported by laboratory experiments in which scientists have replicated briefly and approximately the conditions thought to exist inside ice giant planets and observed diamond formation occurring. The physics allows it. The chemistry allows it. Whether it happens at the scale and in the manner theorized inside Neptune is still being debated, but the possibility sits there patient and extraordinary. A world where it rains diamonds, not as poetry but as a genuine scientific hypothesis, grounded in real experiments, with real materials, under real pressure. The interior of Neptune may be doing something so extreme it sounds invented. Even as you rest right now somewhere in the darkness, beyond the reach of any telescope you could build in a lifetime, diamonds may be forming and falling through the interior of a blue planet slowly in silence. The universe does not reserve its most extraordinary processes for places we can easily see. It does what it does, at every scale in every corner, whether or not anyone is watching. The diamond rain, if it exists, has been falling for billions of years without an audience. It will continue falling long after every instrument we have built has gone quiet. There is something deeply settling in that. Not lonely settling. The universe is not performing for us. It is simply being what it is, in full everywhere all at once. And occasionally, we catch a glimpse of one small part of it and call that glimpse a discovery. The rest continues unhurried and complete with or without our attention. Only one spacecraft has ever visited Neptune. Voyager 2, launched in 1977, reached Neptune in August of 1989, 12 years after leaving Earth. It did not stop. It could not stop. It passed through the Neptune system at extraordinary speed, making its closest approach, and then continuing outward past the planet, past the moons, into the space beyond. The entire close encounter lasted roughly 12 hours. 12 hours to observe a world that had been known for over 140 years but never seen up close. 12 hours to photograph the storms, the rings, the moons, the blue atmosphere in detail for the very first time. Scientists had prepared for years, knowing the window would be brief, knowing there would be no second pass. Everything we know about Neptune's rings, about the structure of its atmosphere, about most of its moons, nearly all of it, came from those 12 hours. One brief window, one pass, one chance. And we used it carefully. The data Voyager 2 gathered at Neptune did not arrive instantly. Traveling at the speed of light, a signal from Neptune's distance still takes over 4 hours to reach Earth. The images and measurements Voyager 2 was sending back as it flew through the Neptune system were already ancient by the time they arrived, snapshots of a moment that had passed hours before anyone on Earth could see them. Scientists watching the data come in were seeing the past, not metaphorically, literally. The Neptune they were observing on their screens was Neptune as it had been 4 hours earlier, the storm and the moons and the rings already continuing to move and change in ways that would take another 4 hours to report. That delay is not unique to Voyager. Every observation of Neptune, every image taken by every telescope since discovery, shows Neptune as it was minutes or hours ago, never as it is right now. We have never seen Neptune in the present tense, only ever as a letter written far away that takes a long time to arrive. Everything we know about Neptune's moons came largely from those few hours Voyager 2 spent in the system. Before the flyby, Neptune was known to have 2 moons. Triton, discovered in 1846, just weeks after Neptune itself was found, and Nereid, discovered in 1949. When Voyager 2 arrived, it discovered 6 more, in rapid succession, small, dark, irregular worlds tumbling close to the planet in orbits no Earth-based telescope had resolved. Since then, additional moons have been found through careful reanalysis of old images and new deep sky surveys. But the detailed knowledge, the shapes and surface features and orbital mechanics belongs almost entirely to that one brief visit. There are moons of Neptune whose surfaces no instrument has ever properly seen. Worlds with names and orbital data and almost nothing else. They exist in our records as gravitational facts, as points of light, as entries in a catalogue. The universe contains far more named unknowns than most people realize. Naming something is often just the beginning of a very long introduction. Somewhere in the deep interior of Neptune, diamonds may be falling. Not quickly, not dramatically. Slowly, the way snow settles through still air on a windless night, each crystal sinking through layers of compressed fluid toward the core, accumulating over billions of years into something that has no name yet in ordinary language. The process, if it is happening, has been continuous since Neptune was young, since before Earth had oceans, since before the first living cell divided in some warm, shallow sea. There is a kind of patience in that image that is difficult to hold and worth trying to. A world quietly doing something extraordinary in its interior in the dark with no audience for longer than life has existed on this planet, not performing it, not waiting to be seen, simply doing what the physics of that place requires, the way water flows downhill, the way stars burn hydrogen, the way all things follow the rules of the place they inhabit. The diamond rain does not need to be witnessed to be real. And that, perhaps, is the most extraordinary thing about it. Neptune's magnetic field is strange. Most planets with magnetic fields generate them from the motion of conducting material near their core on Earth. That means liquid iron in the outer core, churning slowly and producing a field that aligns fairly closely with the steel planet's rotational axis. The North Magnetic Pole and the geographic North Pole are not far apart. Neptune's magnetic field is tilted 47 degrees away from its rotational axis. That is not a small offset. It means the magnetic poles sit far from the geographic poles, and the field itself is not centered on the planet's interior the way Earth's is. It bulges, shifts, and varies in a way that produces a deeply asymmetric field, stronger in some regions, weaker in others, wrapped around the planet in an irregular, lopsided pattern. What generates this field is still not fully understood. It likely originates in the layer of hot pressurized water and ammonia that exists deep in Neptune's interior, a conducting fluid generating magnetism through its motion. But the exact mechanism, the reason for the tilt, the reason for the asymmetry, remains an open question. Neptune's magnetic field is one of the things the universe is still keeping to itself. The source of Neptune's magnetic field may not be its core at all. On Earth, and on most planets where magnetic fields have been studied, the field originates deep in the interior, close to the center, where conditions are most extreme. Neptune appears to be different. Current models suggest the magnetic field is generated not at the core, but in a conducting layer much closer to the surface, in the pressurized ocean of water and ammonia that sits between the rocky core and the outer atmosphere. If that is correct, it changes the way scientists think about how planetary magnetic fields can form. Neptune would not be an exception to a rule, it would be evidence that the rule has more room in it than previously thought. Every time a planet does something unexpected, the models expand to include it. The universe is not wrong when it contradicts our expectations. It is simply showing us where our understanding ends and something more interesting begins. There is no surface on Neptune to stand on. Descend through the outer atmosphere, through the methane haze, through the layers of hydrogen and helium cloud, through the bands of wind, moving faster than anything on Earth, and there is no moment where solid ground appears beneath you. The atmosphere thickens gradually into something denser, hotter, more pressurized, until the distinction between gas and liquid becomes meaningless. Somewhere below the cloud layers, Neptune becomes a vast hot ocean, not of water as we experience it, but of water and ammonia and methane, compressed into a state that behaves like neither liquid nor gas in any ordinary sense. A superheated fluid, pressing in every direction simultaneously with no surface, no shore, no edge. It extends inward until it reaches the rocky, icy core at the planet's center, a core roughly the size of Earth, surrounded by an ocean with no surface, wrapped in an atmosphere with no ground. Neptune is a world where inside and outside are the only directions that matter, and even those blur slowly as you descend. Neptune's moon, Proteus, is darker than coal. It reflects only about 1/10 of the sunlight that reaches it, one of the lowest reflectivities of any object in the solar system. If you held a piece of its surface material in your hand in full daylight, it would appear almost black, absorbing nearly everything the sun sent toward it, and returning almost nothing. Proteus was not discovered from Earth. It was found by Voyager 2 during the 1989 flyby, too dark, too small, and too close to Neptune's glare for Earth-based telescopes of that era to resolve. It orbits very close to the planet inside the ring system, completing one orbit in just under 27 hours. Its shape is irregular, battered, scarred with a large impact crater called Pharos that is so wide relative to the Moon's size that the collision which formed it nearly shattered Proteus entirely. A dark, ancient, quietly battered world orbiting close to a blue giant, absorbing almost every photon that reaches it and returning only shadow. Even in shadow, presence is presence. Neptune has a second storm feature, smaller than the Great Dark Spot but distinct in its own way. When Voyager 2 observed Neptune in 1989, alongside the large dark oval of the Great Dark Spot, scientists noticed a smaller, roughly triangular dark feature in the southern hemisphere. They called it Dark Spot 2. It was accompanied by a small, bright companion cloud that hovered near it, moving with it through the atmosphere like something attached. Unlike the Great Dark Spot, Dark Spot 2 was not circular or oval. It had an irregular shape, and its behavior suggested a different kind of atmospheric dynamic, less a stable vortex and more a localized disturbance in the wind layers. Both storms were gone by the time Hubble looked in 1994. Neptune appears to generate and dissolve these dark features on timescales of years rather than centuries. They form, they persist for a time, and then the atmosphere reclaims them, leaving no trace of the structure that existed there before. The atmosphere is always changing. It simply does not announce it. The winds on Neptune blow in the opposite direction of its rotation. The planet spins from west to east, the same general direction as most planets in the solar system. But in Neptune's upper atmosphere, the dominant winds blow from east to west, against the rotation retrograde, moving in the direction opposite to the planet's spin. This is deeply counterintuitive. On Earth, the relationship between planetary rotation and atmospheric circulation is complex, but generally follows patterns tied to the planet's spin. Neptune's atmosphere seems to operate by a different set of priorities, with the winds finding their own direction regardless of which way the planet beneath them is turning. The exact reason is still debated. The internal heat driving the atmosphere may be strong enough to override the rotational effects that shape circulation on other planets. Or there may be dynamics in the deep atmosphere that redirect momentum in ways that are difficult to model from the outside. Whatever the cause, Neptune's winds go their own way. There is something quietly independent about that. A planet spinning one direction while its atmosphere moves the other, each following its own nature, the whole system somehow holding together anyway. Neptune is the densest of the four ice giants. Ice giants is the category that includes Neptune and Uranus planets, made primarily of materials that are neither the light gases of Jupiter and Saturn, nor the rock and metal of Earth and Mars, but something in between: water, ammonia, methane in compressed exotic states, wrapped in thick gaseous atmospheres. Among those two worlds, Neptune is the denser one. Despite being slightly smaller than Uranus in terms of diameter, Neptune has more mass packed into that smaller volume, a difference that points toward a slightly different interior composition, a slightly different ratio of rocky material to fluid, a slightly different history of formation. The difference is subtle. Standing next to each other in space, the two planets would look broadly similar: large, blue, distant, shrouded in atmosphere. But the density difference hints at something deeper, some divergence in their pasts that produce two worlds that look alike and are not quite. Similar surfaces can hold very different interiors. That is true of planets. It is true of most things. Beneath Neptune's clouds, something vast and hot presses inward from every direction. Not the kind of heat that arrives from outside, not sunlight warming a surface, not radiation reaching down through an atmosphere. This heat rises from within, generated by the slow compression of material that has been settling toward the core for billions of years. It moves upward through the fluid interior the way warmth moves through water on a stove. Not quickly, not in straight lines, but in great rolling currents that carry heat from the deep interior toward the outer layers. Those currents are thought to be one of the engines driving Neptune's extraordinary winds. On Earth, the difference in temperature between the equator and the poles drives much of our weather. Warm air rising, cool air sinking, the whole system circulating because heat and cold exist in the same atmosphere, and try to find balance. Neptune has an analogous process, but driven from below rather than from the side. Internal heat pushing outward through a fluid world, stirring the atmosphere from beneath in ways that produce wind speeds nothing else in the solar system can match. Neptune's weather is not caused by the Sunday. It is caused by Neptune itself. The oxygen in your lungs right now was forged in the heart of a star that died before our solar system was born. Not the Sun, an older star, one that lived its full life and ended in an explosion that scattered its material across space. That scattered material eventually joined the cloud of gas and dust that gravity slowly gathered into our solar system. Some of it became Neptune. Some of it became Earth. Some of it became the air moving in and out of your body at this very moment. You are breathing the remnants of a star. That is not a metaphor dressed in science. It is the actual history of the oxygen atoms entering your blood right now, traced backward through time to a stellar furnace that no longer exists in a location that is now empty space. The connection between your body and the cosmos is not philosophical. It is chemical. It is documented. It is as real as the weight of your body against whatever is holding you right now. The universe did not send that oxygen to you deliberately, but it arrived nonetheless. And here you are using it in the quiet of wherever tonight has placed you. Neptune's atmosphere has distinct layers, each with its own character. The outermost layer is the thermosphere, thin, extended, extraordinarily hot relative to the layers below it, absorbing high-energy radiation from the sun and from space beyond. Below that sits the stratosphere, where temperatures drop and methane begins to condense into haze. Beneath the stratosphere lies the troposphere, the layer where most of the visible weather occurs, where the clouds form and the great winds blow and the dark storms emerge and dissolve. Each layer behaves differently. Each has its own temperature profile, its own chemistry, its own relationship to the layers above and below it. The clouds visible in images of Neptune, the white streaks and patches that stand out against the deep blue, exist in the troposphere, made of methane ice crystals that form where temperatures are cold enough to freeze the gas into solid particles. They drift on those extraordinary winds, forming and dissolving on timescales of hours. A cloud on Neptune might exist for less time than a good night's sleep. Born from freezing gas, carried on impossible winds, dissolved back into the atmosphere before anyone could name it. Neptune's white methane clouds form and dissolve within hours. They appear in images as bright streaks and patches against the deep blue atmosphere, brilliant white, sharply defined, vivid enough to stand out clearly, even against a planet whose color is already extraordinary. But they are temporary. The conditions that allow methane to freeze into ice crystals are specific and narrow, and as the clouds drift on the wind, shifting into regions of slightly different temperature or pressure, they evaporate back into gas and disappear. Hours, sometimes less. There is something quietly affecting about that brevity. A cloud forming in an atmosphere 2.7 billion kilometers from Earth, existing for a few hours, dissolving without record, unseen by anyone on a planet that will continue its orbit for billions of years after every human observer has gone. The universe is full of things that exist completely and briefly and leave no trace. That does not make them less real while they last. It may in some way make them more worth noticing. Neptune is currently in its southern summer. That season began by astronomical reckoning in 2005, and it will continue for more than 40 Earth years before giving way to autumn. The concept of a season that lasts longer than a human generation is difficult to hold in ordinary imagination. A child born at the beginning of Neptune's current summer would be middle-aged before it ended. The seasonal changes on Neptune are subtle compared to Earth's. There is no ice melting, no vegetation responding, no migrating animals following the warmth. But there are measurable changes in the atmosphere. The southern polar region brightens during southern summer as increased solar heating, faint as it is, alters the chemistry and cloud cover of that hemisphere. Instruments on Earth and in space have been tracking those changes carefully. Each observation adds to a picture that will take generations to complete a full Neptunian seasonal cycle spanning 165 Earth years. of which human observation has covered less than 2 complete circuits since the planet's discovery. We are still very early in understanding what Neptune does with its time. Neptune was named before anyone knew it was blue. When Johann Galle confirmed the planet's existence in Berlin in 1846, working from the coordinates Leverrier had calculated, there was no technology available to determine the planet's color from Earth. The name Neptune, after the Roman god of the sea, was chosen for reasons of tradition and mythology, consistent with the convention of naming planets after gods of the ancient world. It was only much later, as telescope technology improved, and eventually as spacecraft visited the outer solar system, that Neptune's extraordinary blue color became fully apparent. The name turned out to be extraordinarily fitting. The deep oceanic blue of Neptune's atmosphere, caused by methane-absorbing red light and reflecting blue back into space, gives the planet a color that genuinely resembles the deep ocean on a clear day. A name chosen without knowing became a description that could not have been better chosen. Sometimes the universe arranges coincidences so apt they feel deliberate. They are not, which somehow makes them more beautiful. 2 men in 2 different countries found Neptune with mathematics alone, and neither knew the other was looking. John Couch Adams in England and Urbain Le Verrier in France both began their calculations around the same time. In the mid-1800s, both working from the same anomaly in Uranus's orbit, both arriving at coordinates pointing to the same region of sky. Adams finished first but struggled to get observatories to act on his predictions. Le Verrier sent his coordinates to Johann Galle in Berlin, who searched that same night and found the planet within an hour. The discovery triggered a genuine international dispute over priority: who deserved credit, whose calculation was more accurate, whose prediction had been made first. The argument drew in national pride, scientific institutions, and personal reputations. Eventually, history settled on acknowledging both men. 2 minds working in isolation, arriving at the same place in the dark. There is something in that parallel which extends beyond astronomy, the quiet evidence that understanding, when pursued carefully enough, tends to converge on the same truths, regardless of who is doing the pursuing. The universe had one answer. Both men found it. Neptune's seasons last more than 40 Earth years each. 4 seasons in one Neptunian year means 4 periods of roughly 40 to 41 Earth years apiece, each one longer than many human careers, longer than the time between a person's birth and the arrival of middle age. Spring on Neptune begins, and most people alive when it starts will still be alive when it ends. Summer follows, and then autumn, and then a winter that outlasts generations. The idea of weather that operates on generational timescales is one of the places where Neptune most quietly resists ordinary imagination. And yet, the planet is not indifferent to its seasons. Measurements show real atmospheric responses to the slow shift in the angle of sunlight, reaching different latitudes. The chemistry of the clouds changes. The brightness of certain regions shifts. Neptune responds to its seasons the way all worlds respond, with the full complexity of its atmosphere, just stretched across a timeline that makes human seasons feel like the blink of an eye. 40 years of summer, and somewhere in the middle of it right now, Neptune drifts through the long, warm stretch of its southern afternoon, unhurried and blue. Neptune was named for the god of the sea before anyone had seen its color. But there is a deeper layer to that coincidence, worth sitting with quietly. The ancient Romans imagined Neptune as the force beneath the water, not the surface of the sea, which was visible and known, but the vast, pressurized, lightless depth below it, the part of the ocean that no one had seen, the part that operated by its own rules, indifferent to weather and ships and the concerns of the world above. That description fits the planet extraordinarily well. Neptune is not a world of surfaces. It is a world of interiors, of layers pressing inward, of fluids at pressures no human instrument has ever directly measured, of chemistry, happening in the dark at temperatures that belong to a different category of experience entirely. Like the deep ocean, the god was named for Neptune keeps most of itself hidden. What we see, the blue face, the white clouds, the dark storms is only the outermost skin of something far stranger beneath. A name chosen from mythology for a world not yet colored in turned out to describe not just the appearance, but the nature of the thing itself. Some intuitions reach further than they know. Two mathematicians found the same planet without knowing the other was looking, but there is a detail in that story that tends to get quietly lost in the telling. Adams had completed his calculations and submitted his predicted coordinates to the Astronomer Royal of England, George Biddell Airy, in 1845. Airy was skeptical. He had questions about Adams's method. He delayed acting on the prediction, and the delay stretched from weeks into months. By the time a search was organized from England, Leverrier had already sent his coordinates to Gall. Gall had already searched, and Neptune had already been found. England had the prediction first. Germany made the discovery. France received the credit. The history of science is full of moments like this, where the distance between a correct idea and a confirmed discovery is not mathematical or observational, but institutional, personal, a matter of who believed whom and when. Ideas that arrive ahead of the willingness to act on them sometimes have to wait. Neptune waited. It had been there all along, exactly where the math said it would be, patient as only planets can be. Galileo observed Neptune in 1612. He recorded it in his notebooks during observations of Jupiter, noting a faint star near Jupiter's position that appeared to move slightly between observations. He saw it again in 1613. He even noted that it appeared to have shifted relative to a nearby fixed star. He did not realize what he was looking at. The motion he observed was real. Neptune was moving as planets do relative to the background stars. But Galileo was focused on Jupiter and its moons. The great discovery of that era and the faint moving point did not register as a planet in need of investigation. It was recorded and set aside. Neptune passed through Galileo's field of view more than 200 years before it was officially discovered, seen by one of history's greatest observers, and not recognized for what it was. There is something deeply human in that, seeing something without yet having the framework to understand it. The observation was correct. The interpretation waited for the right moment, the right question, the right mind prepared to ask it. Sometimes the discovery and the seeing happen centuries apart. Even as you rest right now, consider how many things you have seen without yet having the framework to understand them. Not as a failure, as a condition of being alive inside a universe larger than any single mind can hold. Galileo was one of the most extraordinary observers who ever lived. He looked at Neptune and wrote it down, and moved on. Understanding arrives when it is ready, carried by the accumulation of everything that came before it. No single mind holds all the pieces. Each observer contributes what they can see from where they stand, and the picture assembles itself slowly, across time, across generations, across the patient accumulation of careful looking. You are part of that accumulation too. Every moment of genuine attention to the sky, to the world, to the quiet facts of things, adds something to the long, unhurried project of understanding where we are. It does not have to be dramatic to matter. Neptune's rings were only confirmed to exist in 1989. There had been hints before Voyager 2 arrived. Stellar occultation observations, watching what happens to the light of a distant star as Neptune passes in front of it, had detected unexpected dips in brightness that suggested something was blocking the light near the planet. But the dips were inconsistent, appearing on one side of Neptune but not the other, which led to the idea that Neptune might have arcs rather than complete rings. The confusion was real, and the debate was genuine. When Voyager 2 finally passed through the Neptune system and pointed its cameras back toward the planet, the rings appeared clearly faint, dark, complete circles, with the arcs that had confused earlier observations visible as brighter clumps within the outermost ring. The mystery resolved itself into something more interesting than either hypothesis had predicted. Not arcs, not uniform rings, both somehow at once. The universe often resolves apparent contradictions, not by proving one side right, but by revealing that both sides were describing different parts of the same real thing. Each of Neptune's rings is named after a person, The innermost ring is called Gaia, after Johann Gaia, who confirmed Neptune's existence on the night of September 23, 1846. Moving outward, the next ring is Le Verrier, named for the French mathematician, whose calculations directed Gaia's telescope. Then comes Lassell, named for William Lassell, the English astronomer who discovered Triton just weeks after Neptune itself was found. Then Arago, named for François Arago, a French scientist who supported Le Verrier's work. And finally the outermost ring Adams, named for John Couch Adams. 5 rings, 5 names, 5 people connected to the discovery of a world they could barely see. There is something tender in that practice, the habit of attaching human names to features of the cosmos, placing the people who looked up alongside the things they found. It does not make the rings any less vast or any less ancient. It simply acknowledges that the knowing of a thing is part of its history too. The rings were there long before those names were given. But the names remember the looking. The Adams ring, Neptune's outermost, holds its arcs together in a way that should not, strictly speaking, work. Ring particles in orbit around a planet experience differential gravitational forces. Inner particles orbit slightly faster than outer ones, and over time this tends to spread material evenly around the ring rather than letting it clump. The arcs in the Adams ring have persisted for decades of observation without spreading out the way orbital mechanics would predict they should. The leading explanation involves gravitational resonance with Galatea, a small inner moon of Neptune whose orbital period is in a specific ratio with the orbital period of the arc material, a ratio that creates a repeating gravitational nudge, keeping the particles confined within a narrow range of the orbit rather than drifting freely around it. But the model does not fully account for everything observed. The arcs appear to be slowly changing, possibly degrading, and the resonance mechanism may not be stable over very long timescales. The rings are being held together by something we understand partially and not yet completely. Most things examined closely enough turn out to be held together that way. Neptune's gravity reaches far beyond its visible rings. In the outer solar system, beyond the orbit of Neptune, lies the Kuiper Belt, a vast region of icy objects, some small, some large enough to be considered dwarf planets, stretching from roughly Neptune's orbit outward for an enormous distance. Neptune's gravity shapes the inner edge of that belt, herding objects into specific orbital patterns, clearing some regions and populating others through resonances that operate over millions of years. Pluto, the most famous Kuiper Belt object, is locked in a gravitational resonance with Neptune. For every 2 orbits Neptune completes around the Sun, Pluto completes exactly 3. This relationship has kept Pluto stable in its orbit for an immense span of time, preventing the kind of close encounter with Neptune that would send it careening into a different path. Neptune is in this sense a shepherd, not just of its own moons and rings, but of an entire population of distant icy worlds organized and maintained by gravity, operating across distances so large that the objects being shepherded cannot be seen from Earth without careful effort. Influence does not require proximity. Neptune shapes things it will never touch. Neptune holds its rings with a kind of gravity that asks nothing in return. The rings do not know they are being held. The icy particles and dark organic clumps moving in their slow circles around the planet have no awareness of the force organizing them, keeping them from drifting outward into the dark, maintaining the faint architecture of those shadowy circles against the slow pressure of orbital decay. Neptune simply exists, massive and blue, and the gravity that follows from that existence does the rest. That is what gravity is in the end, not a reaching or a grasping, a consequence of presence, a natural result of mass existing in space, curving the geometry around it in ways that draw other things into relationship without effort or intention. The rings are held. The moons are held. The distant Kuiper Belt objects are organized and shepherded. All of it happens not because Neptune is trying to do anything, but simply because Neptune is there. Presence at sufficient scale organizes the world around it. And perhaps that is true at smaller scales too, that simply being present fully and quietly shapes what comes near in ways that require no effort at all. Only continuity. Only the patient fact of being there. Deep in Neptune's interior, something hums. Not in any way a human ear could detect, and not through any medium that sound as we experience it could travel. But low-frequency pressure waves move through Neptune's atmosphere, rippling outward from disturbances deep inside the planet, propagating through the cloud layers in patterns that instruments could, in principle, detect and measure. This is not unique to Neptune. The Sun oscillates in similar ways, its surface rising and falling in patterns driven by the churning of its interior, a kind of stellar heartbeat that helioseismologists study to understand what is happening deep inside, where no instrument can directly reach. The same principle, applied to planets, is called seismology, and scientists have used it on Earth for decades to map the interior structure of our own world. Neptune has never been studied this way directly. No instrument has ever sat in its atmosphere long enough to measure those pressure waves carefully. But the waves are almost certainly there, moving through the cloud layers, carrying information about the interior that no other method can reach. A planet communicating its own depths in a language we have not yet had the instruments to hear. Triton's surface is one of the coldest places ever measured in the solar system. The temperature at Triton's surface sits at around -235 degrees Celsius, just 38 degrees above absolute zero, the theoretical point at which all thermal motion stops entirely. At that temperature, nitrogen, which makes up most of Earth's atmosphere and exists as an invisible gas on a mild day, freezes solid and lies on Triton's surface as pink-tinged ice. The pink color comes from organic compounds, carbon-based molecules, created when cosmic radiation interacts with the nitrogen and methane ices over long periods of time, slowly building up a thin layer of complex chemistry across the frozen surface. Absolute zero is the coldest anything can possibly be. Triton sits 38 degrees above that limit, which sounds like a meaningful margin until you consider that the temperature of a comfortable room sits roughly 300 degrees above absolute zero. Triton is not 38 degrees from absolute zero in the way a cold winter morning is a few degrees from freezing. It is 38 degrees from the edge of all motion, and yet something moves beneath it. Triton is geologically active. Beneath a surface cold enough to freeze nitrogen solid, something in Triton's interior appears to be generating enough heat to maintain a liquid layer, possibly a subsurface ocean of liquid water mixed with ammonia kept from freezing by psi. A combination of tidal heating from Neptune's gravity and residual heat from Triton's own interior. This possibility has not been confirmed. The evidence is indirect. The smoothness of parts of Triton's surface suggesting geological resurfacing, the presence of the nitrogen geysers that require some energy source, even if that source is ultimately solar, the general patterns of the terrain observed by Voyager 2. But the possibility is taken seriously. A moon so cold its surface freezes nitrogen, potentially harboring liquid water beneath the ice in the farthest reaches of the planetary solar system. Heated partly by the gravity of the blue giant it was captured by billions of years ago. Life, as far as we know, requires liquid water. Scientists are careful not to leap from liquid water to life. But the ingredients that make life possible are not rare. They appear in the most unexpected places. Even here, even this far out. Triton was almost certainly born somewhere else. The current leading hypothesis places its origin in the Kuiper Belt, the vast population of icy objects that orbits beyond Neptune, remnants of the early solar system that never gathered into a planet. Triton, in this view, was once a Kuiper Belt object, a large icy world drifting in its own orbit around the Sun, following its own path through the outer solar system, unattached to any planet. Then Neptune's gravity intervened. The mechanism by which Neptune could have captured something as large as Triton is still debated. One possibility involves a binary system. Triton may once have had a companion object orbiting close to it, and when the pair came near Neptune, gravitational interactions separated them, sending the companion away and trapping Triton in orbit. The companion, in this scenario, continues somewhere in the outer solar system to this day, unknown and unnamed, a moon born as a wanderer, captured by gravity, still carrying the evidence of its origins in the direction of its orbit. Every path carries the history of how it began. Even as you rest right now, you are being held by gravity in exactly the way Triton is held by Neptune. Not with the same force, not with the same consequence. But the principle is identical mass, attracting mass geometry, curving around presence, the ground beneath you and the planet above you, engaged in the same quiet conversation that Neptune and Triton have been having for billions of years. You do not feel the holding because it is constant, because there has never been a moment in your life when it was not there. Gravity does not announce itself. It simply maintains. It simply continues. Triton does not feel the holding either, and yet both of you are held completely in every moment by a force that asks nothing and releases nothing, and simply persists as long as mass exists in the universe. There is a kind of safety in that if you let yourself feel it. The ground is not going anywhere. Neither are you. Neptune and Uranus look similar from a distance. Both are large. Both are blue. Both belong to the category called ice giants, dominated by water, ammonia, and methane in exotic states, rather than the hydrogen and helium that fill Jupiter and Saturn. They are often spoken of together, paired as the outer twins of the solar system, the distant cousins of the gas giants, closer to the Sunday. But the differences between them are real, and still not fully explained. Neptune is more active. Its atmosphere churns with storms and winds that Uranus, despite being broadly similar in composition and size, does not produce. Uranus is remarkably, almost strangely calm. Its atmosphere flat and featureless compared to Neptune's, its winds gentler, its storms rarer and less dramatic. The difference is thought to be connected to internal heat. Neptune radiates significantly more heat from its interior than Uranus does. Uranus, for reasons that are still debated, appears to have retained very little internal heat, or to have lost it in ways that are not yet understood, possibly through a large impact early in its history, that may also explain why it rotates. On its side, two similar worlds, one calm, one turbulent. The difference, as so often, lies in what is happening inside. Neptune's atmosphere contains hydrogen, helium, and methane, a recipe shared in broad outline with Uranus and with the early solar nebula from which all the planets formed. Hydrogen and helium are the most abundant elements in the universe. They were produced in the first few minutes after the Big Bang, before stars existed, before galaxies existed, before any structure larger than an atom had formed. Every hydrogen atom in Neptune's atmosphere has existed in one form or another since near the beginning of everything. The methane is younger, formed later, when carbon produced in stellar cores was available to combine with hydrogen. But it too has been cycling through various forms for billions of years, long before it became part of the atmosphere of a blue planet at the edge of the solar system. Neptune's atmosphere is, in a sense, a sample of the oldest chemistry in existence. Ancient elements gathered by gravity, arranged into clouds and winds and storms by processes that have been running for 4.5 billion years. The air on Neptune has been air in one form or another for nearly as long as the solar system has existed. Some things persist, not by being unchanging, but by continuously becoming something new from the same old ingredients. There is a cloud on Neptune that moves faster than everything around it. Astronomers who studied Voyager 2's images of Neptune in 1989 noticed a small, bright white feature in the southern hemisphere that appeared to be racing around the planet at a speed noticeably faster than the large, dark storms nearby. They called it the Scooter, an informal name that stuck because it described exactly what the feature appeared to be doing: scooting, moving with a kind of brisk, purposeful energy against the backdrop of slower atmospheric features. The Scooter was a cloud system, probably sitting at a different altitude than the dark spots, riding a different band of wind that moved at its own speed relative to the features above and below it. Neptune's atmosphere operates in distinct layers, each with its own wind regime, and a cloud anchored in one layer might move at a pace completely different from a storm anchored in another. When Hubble looked at Neptune again in the years following the Voyager flyby, the scooter was gone. Whether it dissipated, changed form, or simply became undetectable is not known. A small, fast, bright thing noticed once, recorded carefully, and then lost. Some things are only ever glimpsed. The scooter has not been seen since 1989. That absence is not unusual for Neptune. The planet's atmosphere rearranges itself on timescales short enough that features visible during the Voyager flyby bore little resemblance to what Hubble found when it looked 5 years later. Storms that were clearly defined in 1989 had dissolved. New features had appeared. The white clouds that had been bright and sharp in Voyager's images had shifted and reformed into different configurations. Neptune does not hold still for portraits. There is something worth noticing in that restlessness. The planet is so far away that each observation requires extraordinary effort. Specialized telescopes, careful scheduling, long exposures, gathering faint light across an immense distance. And what arrives after all that effort is a glimpse of a moment that has already passed, showing features that may already have changed by the time the image is processed and studied. Observing Neptune is always observing the past, always catching something mid-transformation, always seeing a snapshot of a system that never pauses. The universe does not wait for us to finish looking before it moves on. Some of Neptune's smaller moons were hiding in plain sight for decades. After the Voyager 2 flyby identified 6 new moons beyond the 2 already known, astronomers continued searching through the years that followed, using Earth-based telescopes and later space-based observatories. Several additional small moons were found, but some of them had been quietly present in older photographic data all along, their faint signals lost in the noise or overlooked in images taken for other purposes. One moon, Hippocamp, was discovered in 2013 by a team carefully reanalyzing archival images from the Hubble Space Telescope. It had been present in images taken years earlier, its tiny point of light simply not noticed amid the complexity of Neptune's inner system. Once researchers knew what they were looking for and where, it became visible in data that had been sitting in archives for years. There is a particular quality to that kind of discovery, finding something not by looking harder, but by looking again with slightly different attention at something already in hand. It suggests that knowledge is not always waiting beyond the edge of what has been observed. Sometimes it is waiting inside the observation, already made patient and unnoticed, until someone arrives with the right question. What we already have often contains more than we have found in it yet. Hippocamp is a small moon, and it likely has a small origin story. Its orbit places it very close to a much larger moon called Proteus, the dark, coal-black world that Voyager 2 discovered in 1989. Proteus bears the scars of an enormous ancient impact, a crater called Pharos, so wide it nearly shattered the moon when it formed. The debris from that collision scattered in all directions. Scientists believe Hippocamp may be a fragment of that event, a piece of Proteus broken off by the impact that settled into its own orbit around Neptune, rather than drifting away into space or falling back to the surface. If that is correct, Hippocamp has been orbiting near its parent moon for an immense span of time. A quiet, dark, small companion, born from violence and settled into patience, circling Neptune in the inner part of the ring system, without anyone knowing it was there for most of the time humans have been studying the planet. A world born from a collision, surviving as a small and steady presence. There are worse ways to persist. Naiad, one of Neptune's inner moons, moves with extraordinary speed. It orbits so close to Neptune, and so quickly, that it completes one full orbit around the planet in just under 8 hours faster than Neptune itself rotates. While the planet beneath it is still completing less than half a turn, Naiad has already gone all the way around. It laps the planet's rotation the way a fast runner laps a slower one on a circular track, consistently, continuously, without pause. This places Naiad deep inside Neptune's inner system, threading its path through the gaps and edges of the ring material close enough to the planet that its motion is governed almost entirely by Neptune's gravitational pull and, relatively little, by the influence of other moons. Naiad's orbit is also tilted and irregular, not a clean circle, but a path that weaves slightly up and down relative to Neptune's equatorial plane. This wobble is thought to be the result of gravitational interactions with another nearby moon, Thalassa, whose presence nudges Naiad's path in a repeating pattern that has been stable for a very long time. Two small moons dancing around each other through the rings of a blue giant, each one shaping the path of the other without ever coming close enough to touch. Naiad's path weaves through Neptune's inner ring system like a needle pulling thread. That image is not purely poetic. The orbital mechanics of small moons embedded in or near ring systems involve real physical interactions. The moon's gravity disturbs nearby ring particles. The ring particles' collective gravity nudges the moon in return, and over time these mutual influences settle into patterns that can be surprisingly stable. Naiad has been threading its particular path for an enormous span of time, its orbit shaped by the rings shaping them. In return, the whole system locked into a kind of slow, intricate conversation. This is one of the ways ring systems and their associated moons are understood to evolve, not in isolation, but in constant gravitational dialogue, each component responding to all the others, the whole system finding configurations that can persist across millions and billions of years. The result is something that looks from a distance simply like a planet with rings and moons. Up close, it is a dynamic system of mutual influence, continuously negotiating its own structure through the patient language of gravity. Everything in Neptune's system is in relationship with everything else. Nothing orbits alone. Everything in Neptune's system moves in a balance that has taken billions of years to find. The moons pull at the rings. The rings constrain the moons. The planet holds everything. And the whole arrangement, the dark arcs, the fast inner moons, the captured Triton spiraling slowly inward, the faint outer moons tumbling in irregular paths, is a system that arrived at its current configuration through an immense history of collisions, captures, resonances, and gradual settling. It did not begin this way. The early Neptune system was almost certainly more chaotic, more crowded with debris, more prone to collisions, less organized by the resonances that now give it structure. Time and gravity worked together to produce what exists now, discarding what could not persist and keeping what could. What we see when we look at Neptune today is not Neptune as it began. It is Neptune as it has become shaped by everything that happened to it, organized by the long patience of physical law, still changing slowly in ways that will produce a different system billions of years from now. All stable things were once unstable. All order is earned slowly from chaos. Even as you rest right now, you are somewhere inside that same process. Not the chaos of early planetary formation, but the slower, quieter process of things finding their configuration, settling into patterns that can persist, being shaped by forces that operate over longer timescales than a single life can. Observe. The cells in your body are in constant negotiation with each other, maintaining balances that took billions of years of evolution to discover. The relationships you carry, the habits of thought that feel like simply who you are, the rhythms of your days, these too are configurations that arrived at their current form through a long history of adjustment and response. You are, in some sense, a system that has been finding its balance for as long as you have existed. And like Neptune, you are not finished. The balancing continues, quietly, continuously, without requiring your attention to proceed. Rest then. Let the negotiation continue on its own. Neptune's rings glow in infrared light. To ordinary human vision, the rings are essentially invisible, too dark, too faint, too far away to register without instruments, far more sensitive than any eye. But in infrared wavelengths which detect heat rather than visible light, the rings become measurable. They emit a faint warmth absorbed from the distant sun and from Neptune's own radiated heat that instruments can detect and map across the ring system. Infrared observations have allowed scientists to study the composition and temperature of the ring material in ways that visible light observations cannot. The dark organic compounds that make the rings so dim in visible light behave differently in infrared. revealing details about their structure and chemistry that would otherwise remain hidden. There is something quietly affecting in that. A thing invisible to direct perception present nonetheless detectable only by instruments sensitive to a different kind of signal than the eyes use. The rings do not become more real when the infrared camera finds them. They were always there. The instrument simply extended perception far enough to reach what was already present. Much of what is real in the universe falls outside the narrow band of what human senses can directly detect. The world is wider than it looks. Presence without visibility is something the natural world does extraordinarily well. Neptune's rings are one example among countless. Magnetic fields threading through space, invisible and unfelt without instruments. Gravitational waves rippling through the fabric of space-time, passing through every object in the universe, including human bodies, leaving no sensation behind. Dark matter, which appears to make up the majority of the mass in the universe, detectable only through its gravitational effects on things we can see, never directly observed in any other way. The universe is full of things that are present without being visible, full of influences that operate without announcing themselves, full of forces that shape what we can see by acting from somewhere we cannot. Science is in a significant part the project of extending perception beyond the boundaries of the senses, of building instruments that detect what eyes and ears and skin cannot, of asking what is there that we are not yet equipped to notice, and then building the tools to find out. Every discovery of something previously invisible is a reminder that the inventory of real things is always larger than the current list of known things. We are always in the middle of the list. Neptune's moon hippocamp was hiding in archived data for years before anyone found it, but the story of its discovery carries something beyond the simple fact of a moon found. The team that identified it was not conducting a new observation campaign with new instruments pointed at Neptune. They were sitting with data that already existed, looking at images already taken, running new analysis software across an archive that had been accumulated over years of Hubble observations. They found something new in something old. That practice, returning to existing records with new tools and new questions, has produced a remarkable number of discoveries across the history of science. Pulsars were found in archived radio data. Exoplanets have been confirmed in light curves gathered years before anyone searched them for planetary transits. Ancient astronomical observations have been reanalyzed with modern methods to reveal patterns invisible to the original observers. The past is not finished yielding what it contains. Every archive is a field still being harvested. Every old observation is a potential answer to a question not yet asked. The data that exists right now in telescopes and databases and hard drives around the world contains things we have not yet found because we have not yet thought to look for them. Some discoveries are waiting not for new instruments but for new questions. Neptune's moon hippocamp orbits near Proteus, likely born from a fragment of an ancient collision. But consider what that means in terms of time. The impact that gouged Pharos crater into Proteus, the event that may have sent hippocamp spinning into its own orbit, happened billions of years ago, long before the first complex life appeared on Earth. Long before the oceans took their current form. Long before the continents arranged themselves into anything recognizable on a modern map, hippocamp has been quietly orbiting Neptune since before multicellular life existed on this planet. It has circled that blue giant through the entire history of complex life on Earth, through every extinction event, every ice age, every rise and fall of every species that has ever existed on this planet, including the ones that eventually looked up and noticed it was there. A small dark fragment of a larger world, patient beyond any human measure of patience, orbiting in the dark, while an entire biosphere came and went on a small blue planet in the inner solar system. Time at this scale becomes something other than a quantity. It becomes a kind of presence. Even as you rest right now, consider that you are made of matter older than the solar system, living on a planet younger than many of the stars visible tonight, watching a universe that has been running for nearly 14 billion years. Your life measured against those scales is extraordinarily brief. And yet here you are, aware of all of it, capable of holding those timescales in mind, of feeling something in response to them. of finding them beautiful or humbling or both at once. No other arrangement of matter that we know of, not a star, not a planet, not a galaxy, is aware of its own existence in the way that you are. Neptune has been there for 4.5 billion years. It does not know it is blue. It does not know it has moons. It does not know that someone on a small, warm planet far away spent time thinking about it tonight and found it beautiful. That knowing belongs to you. It is not a small thing to be the kind of thing that knows. A mission to Neptune is being seriously discussed. Multiple proposals have been developed over the years by space agencies around the world, outlining what a dedicated Neptune orbiter could accomplish, studying the planet's atmosphere in depth, mapping its magnetic field, observing its moons up close for the first time since Voyager 2 possibly, even deploying a probe into Triton's thin atmosphere. The challenges are significant. Neptune's distance means any spacecraft launched today would take roughly 12 to 13 years to arrive, depending on the trajectory and available planetary alignments for gravity assists. The mission would need to be designed, funded, approved, and built over a period of years before launch, meaning the earliest a realistic mission could arrive at Neptune is sometime in the late 2030s or beyond. The scientists working on those proposals are doing so knowing they may retire before the spacecraft launches and may not live to see it arrive. They are designing something for the future, for researchers not yet in their careers, for a generation of scientists who will inherit the data from a journey that began before some of them were born. That is a particular kind of generosity. The scientists who design a Neptune mission may not live to see its arrival. This is not an unusual situation in the history of planetary exploration. The people who conceived and fought for the Voyager program in the 1960s and early 1970s knew it would take decades for those spacecraft to reach the outer solar system. Some of them did live to see the Neptune flyby in 1989. But the journey consumed more than a decade of their professional lives, and the data it returned continued to be analyzed long after many of them had retired. Science at this scale operates across timescales longer than careers. Ideas are planted in one era, nurtured through many, and harvested in another. The person who writes the first proposal and the person who publishes the final analysis of the data may never meet. They are connected not by shared memory, but by shared purpose, the long, patient project of understanding a place they will never visit. There is something in that chain worth sitting with quietly. Knowledge passed forward like a letter written to someone not yet born. The trust required to begin something you will not finish. The generosity of investing fully in a future you will not entirely inhabit. The universe rewards that kind of patience, slowly and without ceremony. Knowledge passes forward the way starlight does, generated in one place, received somewhere else, across a distance that changes everything, except the thing itself. The light leaving a star right now will arrive at a distant planet millions of years from now. The star itself may be gone by then, but the light will still carry the information it left, with the spectrum, the wavelength, the temperature encoded in color unchanged by the journey, still telling the truth of what it came from, even after an unimaginable distance. Ideas move through time, the way light moves through space. What someone understood clearly and recorded carefully in one century can arrive in another century in a different mind, in a different language, in a different cultural context, and still illuminate, still carry the original insight intact through whatever distance of time separated the writing from the reading. You are right now receiving light that left various sources, years and decades and centuries ago. The books that shaped how you think, the discoveries that changed what you believe is possible, the questions that lodged in your mind and never quite left, all of it traveled to reach you. And whatever you understand clearly and pass on carefully will travel further still. Neptune sits at the edge of what we call the planetary solar system. Beyond its orbit, the organized realm of the 8 planets gives way to something wilder and more diffuse. The Kuiper Belt stretching outward for an immense distance, populated by icy objects in various sizes. Some large enough to be considered dwarf planets, most too small and dark to be seen without the most powerful telescopes available. Neptune is the last of the recognized planets. Everything beyond it belongs to a different category of solar system object, a different chapter of the story. And yet Neptune is not at the edge of the Sun's reach. The Sun's gravitational influence extends far beyond Neptune, past the Kuiper belt, past the scattered disk of objects, beyond that all the way to the Oort cloud, a vast spherical shell of icy bodies thought to surround the entire solar system at distances so great that light from the Sun takes more than a year to reach the outermost parts of it. Neptune is not the end. It is the last familiar landmark before the territory becomes genuinely unmapped. Standing at the edge of what is known and looking outward at what remains unknown is a position with a particular quality to it. Not frightening, not empty, simply open. Beyond Neptune lies the Kuiper belt, then the scattered disk, then the Oort cloud, then the nearest star. Each of those distances represents a different scale of vastness. The Kuiper belt extends from roughly Neptune's orbit to about 50 times the Earth-Sun distance, already a span difficult to hold in imagination. The Oort cloud may extend to as far as 100,000 times that same distance, and the nearest star, Proxima Centauri, sits at a distance that light takes 4 years and 3 months to cross. Voyager 1, the fastest human-made object ever launched, has been traveling for nearly 50 years and has only just reached the very inner edge of interstellar space, still well short of the Oort cloud's outer boundary, still nowhere near the nearest star. The solar system is not a small place with a large universe around it. It is itself an immensity, one that dwarfs every distance a human being has ever physically traveled, every distance any human instrument has covered, and still represents only the tiniest fraction of the larger structure it belongs to. Neptune, from this perspective, is not far away. It is still, cosmically speaking, right next door. The space between Neptune and the Kuiper belt is not empty. This is a common misunderstanding, that the outer solar system beyond Neptune is a kind of void, a dark and featureless gap before the distant belt of icy objects begins. In reality, objects are distributed through that region in smaller numbers than in the Kuiper belt proper, but not zero. Scattered disk objects drift in highly elliptical orbits that take them far beyond Neptune and then swing them back in close. Long-period comets pass through on their enormous loops from the Oort cloud toward the inner solar system and back. The outer solar system is sparsely populated, not empty. Dark and cold and difficult to observe, but occupied, full of objects following their own paths, shaped by the same gravitational forces that govern everything closer in. Emptiness in space is almost always a matter of scale and sensitivity. What looks empty at one resolution reveals structure at another. What seems featureless from a distance contains detail up close. The universe does not do empty particularly well. It fills available space with something, even if that something is thinly distributed and takes extraordinary instruments to find. There is always more there than the darkness suggests. Neptune shepherds the inner edge of the Kuiper belt. This gravitational influence is one of the most significant structural forces in the outer solar system. Neptune's gravity has over billions of years cleared certain orbital regions near its path, and populated others, pushing objects into resonant orbits, where they are protected from close encounters with the planet, or scattering them into the outer solar system when they stray too close. The result is that the inner Kuiper belt has a structure that reflects Neptune's presence even at distances far beyond where Neptune's rings and moons exist. Objects cluster in certain orbital ratios relative to Neptune and avoid others. The distribution of icy bodies across billions of kilometers of space is in part a map of Neptune's gravitational reach over geological time. Pluto is the most famous example of this, shepherding locked in a 2 to 3 resonance with Neptune that has kept it stable for an immense span of time. But there are many others, a whole population of Kuiper belt objects in similar resonances, collectively called Plutinos, all of them dancing in step with Neptune's patient gravitational rhythm. A planet shapes its neighborhood long after the neighborhood ends. Without Neptune, the inner solar system might look very different. This is a hypothesis, rather than a confirmed fact, and scientists approach it with appropriate care. But the general principle is supported by planetary formation models. The presence of a large planet in the outer solar system influences what kinds of objects reach the inner planets and on what timescales. Jupiter is often credited with acting as a shield for Earth, its gravity deflecting or capturing some of the comets and asteroids that might otherwise reach the inner solar system. Neptune plays a comparable role in the outer system, organizing the Kuiper belt population, keeping objects in stable resonances rather than sending them on trajectories that cross the orbits of the inner planets. A solar system without Neptune, or with Neptune in a different position, might deliver more impactors to the inner planets more frequently. The history of bombardment on Earth, and therefore the history of life on Earth, might look different. Neptune has been influencing the conditions for life from 4.5 billion kilometers away, without any connection to life, without any awareness of the inner solar system, simply by being massive and present and governed by gravity. Influence at a distance, over geological time without intention. Neptune formed from the same cloud of gas and dust as every other planet, including Earth. This is a fact so fundamental it is easy to pass over without pausing. The solar system did not form from several different clouds, each producing its own planets independently. It formed from a single cloud, one vast, slowly rotating reservoir of gas and dust that collapsed under its own gravity roughly 4.5 billion years ago. As it collapsed, it flattened into a disk, and within that disk, material clumped together under gravity into the Sun at the center, and the planets distributed outward. Neptune formed in the outer part of that disk where conditions were cold enough for water, ice, and other volatile compounds to exist as solid particles, providing the building material for an ice giant. Earth formed in the inner part, where temperatures were higher and rocky metallic material dominated. Same cloud, same beginning, different neighborhoods, different outcomes. The atoms that make up Neptune's atmosphere and the atoms that make up your body have a common origin, not metaphorically, but physically, in the specific cloud that gravity gathered into this solar system 4.5 billion years ago. You and Neptune are in the most literal possible sense from the same place. The same forces that shaped Neptune shaped the ground beneath the listener tonight. Gravity pulling material together, pressure building in interiors, heat rising and radiating, chemistry evolving over billions of years from simple elements into complex compounds. The processes that built Neptune and the processes that built Earth are not different processes operating independently. They are the same process, the same physical law, acting on the same raw material in the same gravitational system, producing different outcomes because of different local conditions, distance from the Sun temperature, the particular mix of material available at that orbital distance. The ground beneath you right now was shaped by the same physics that shaped Neptune's core. The air you breathe was assembled by the same chemistry that fills Neptune's atmosphere. The warmth of Earth's interior still leaking outward from its own formation is the same phenomenon as Neptune's internal heat. Both worlds still slowly releasing the energy of their own, becoming billions of years after the becoming happened. You are living on a world that shares its origin story with the blue giant at the edge of the solar system. That story is still being told by both of them in different ways at this very moment. Time at the scale of planetary formation becomes something other than time. In ordinary experience, time is the medium through which events occur. One thing happens, then another, and the sequence is what we call history. A human life spans decades. A civilization spans centuries or millennia. These are the scales at which time feels most real and most personal. But 4.5 billion years is not simply a very large number of years. It is a different category of duration entirely, one in which the very meaning of before and after begins to dissolve, in which what looks like a single moment from outside is itself an immensity containing everything. In 4.5 billion years, continents drift across entire oceans. Species appear flourish for tens of millions of years and vanish without trace. Entire evolutionary lineages emerge, diversify into thousands of forms, and collapse back into extinction. The The sun itself has changed. It is brighter now than it was when the solar system formed, and it will continue to brighten until conditions on Earth become too warm for the life currently here. Geological time does not compress into human time by any metaphor. It simply is what it is, vast, patient, and indifferent to the scale we find most comfortable. Neptune has been moving through it all, quietly, for every moment of that span. Neptune's blue is a kind of answer the atmosphere gives to sunlight. Light from the sun arrives at Neptune carrying the full spectrum: red, orange, yellow, green, blue, violet, all of it traveling together across the immense distance from the sun's surface to the outer edge of the planetary solar system. When that light enters Neptune's atmosphere, the methane molecules there absorb the red wavelengths, pulling them out of the beam, converting their energy into heat. What remains, what reflects back into space and eventually reaches the instruments and eyes of observers far away, is predominantly blue. The color is not painted on. It is selected. It emerges from the interaction between the light that arrives and the chemistry that receives it. In a sense, Neptune's blue is a record of what the atmosphere kept and what it gave back. A signature of chemistry written in color, readable from billions of kilometers away. Every color in the natural world works this way, not applied, but emergent, the result of light meeting matter and each responding to the other according to the rules of their interaction. A leaf is not green the way a painted wall is green. It is green because chlorophyll absorbs red and blue and returns the green it does not need. Color is not a property of things. It is a conversation between things and light. Neptune's blue has been waiting in space long before a human eye existed to receive it. The planet has been reflecting that deep, methane-filtered blue outward into space for 4.5 billion years. For most of that time, there was no one to see it. No eyes had evolved anywhere in the solar system. No instrument had been built. The blue traveled outward from Neptune's atmosphere, crossed the darkness, dispersed into space, and arrived nowhere in particular, not received, not recorded, not perceived. It was real nonetheless. This is one of the places where the universe's indifference to being observed becomes something to sit with rather than something to resolve. Neptune's color did not wait for eyes to make it real. It did not become blue when someone finally looked. It was blue in the dark for billions of years, whether or not the blue reached anyone. Reality does not require a witness. The color of a world, the warmth of a star, the orbit of a moon, these things are fully themselves regardless of whether any mind anywhere is attending to them. Perception does not create, it discovers. And what it discovers was already completely there. The first record of Neptune as an observed object is a small smudge of light on a glass photographic plate from 1846. Not a crisp disk, not a blue sphere. A smudge, a point of light slightly larger and slightly different from the points of light around it, recorded on the photographic technology of the mid-19th century, developed in a darkroom somewhere in Berlin on the night it was found. That smudge contained everything. Inside that tiny point of light, invisible to the technology of the time, a storm the size of Earth, winds moving at 2,100 kilometers per hour, 16 moons in various orbits, rings of dark organic material, geysers on a frozen moon, a magnetic field tilted 47 degrees from the planet's axis, an interior hotter than the surface of the Sunday diamonds, possibly, falling through pressurized fluid in the deep dark below the clouds. All of it compressed into a smudge on a glass plate in a city in Germany in 1846. A whole world contained in a point too small to resolve. Distance does not diminish what a thing is. It only changes how much of it you can see at once. Every time something vast is seen from far away, it teaches a different kind of patience. Astronomy is, among other things, a discipline of accepting what distance allows and working carefully within those limits. A planet 4.5 billion kilometers away cannot be walked up to, cannot be touched, cannot be directly sampled, at least not yet, not by any instrument that has ever been sent there. What can be done is to gather whatever light it sends, to analyze that light with extraordinary care, to build models consistent with what the light reveals, and to hold those models with appropriate humility, knowing they are the best current understanding and not the final word. That practice, working carefully within limits, treating partial information as genuinely informative rather than simply insufficient, is not unique to astronomy. It is the condition of understanding almost anything that matters. The people most worth listening to in any field are usually the ones who have learned to work thoughtfully within the limits of what is actually known, rather than filling the gaps with confidence they have not earned. Neptune is 4.5 billion kilometers away, and we know a remarkable amount about it. That knowledge was earned carefully, incrementally, over generations. It is the more trustworthy for that. Neptune does not know it is being watched. This is a simple fact with a particular texture to it worth sitting with slowly. The planet has no awareness of the telescopes pointed at it from Earth, no awareness of the images being taken, no response to the attention directed toward it across an immense distance. It does not perform for observers. It does not simplify itself for understanding. It does not hold still for the photographs or wait for the analysis to finish before changing its atmosphere or moving its storms. It simply continues, and there is something quietly freeing in that. Neptune is not a spectacle arranged for human benefit. It is not a lesson constructed to be understood. It is simply a world doing what worlds do, rotating, orbiting, maintaining its chemistry, generating its winds, holding its moons in their paths with complete indifference to whether any of that is being noticed. The attention we bring to it is ours. The meaning we find in it is ours. The beauty we experience in its blue color and its extraordinary dynamics and its ancient moons is something we generate in response to what is there. Neptune provides the occasion. We provide the wonder. And both are necessary for what happens when we look. Even as you rest right now, Neptune is continuing its orbit without you and without needing you. It has been doing this for 4.5 billion years. It will continue doing it for billions more. The fact that you spent time thinking about it tonight changes nothing about Neptune's path, nothing about its storms, nothing about the slow inward spiral of Triton or the faint arcs of the Adam's ring or the diamond rain falling silently in its interior. And yet the thinking happened. The attention was real. The connection across 4.5 billion kilometers of space, across the extraordinary improbability of a universe producing something capable of wondering about itself. The connection was real too. You did not need to affect Neptune for this to matter. The knowing mattered. The turning of attention towards something vast and ancient and indifferent, and finding it beautiful anyway, that is not a small thing. That is one of the things minds are for. Neptune's rings glow faintly in the infrared, invisible to the naked eye, but present nonetheless. And that phrase, present nonetheless, carries something worth carrying into the rest of this night. The rings do not become more real when an infrared camera finds them. The moons of Neptune did not begin to exist when Voyager 2 photographed them. Triton's geysers did not start erupting when scientists analyzed the images and confirmed what they were seeing. All of it was already fully there, fully itself in the dark and the distance, whether or not any instrument or any mind had ever reached far enough to find it. Presence without visibility is a condition the universe accepts without difficulty. It is perhaps a condition worth accepting too, the possibility that much of what is real and valuable and genuinely there in the world around us exists outside the range of what our attention typically reaches. Not hidden. Not absent, simply not yet looked for, or looked for with instruments not yet sensitive enough to find it. The world is full of things present in the dark. Some of them are waiting for the right kind of looking. A photograph of Neptune taken with a modest telescope today shows a small bluish disk, not the deep saturated blue of Voyager's close-up images, not the dramatic cloud features visible from a nearby spacecraft, but a soft blue point, slightly wider than the stars around it, its disk just barely resolvable in good. Seeing conditions with a large amateur instrument, it is enough to confirm that the planet is there, enough to measure its position and track its slow movement against the background stars, not enough to see the storms or the rings or the cloud features that change from week to week. And yet astronomers continue to look. Amateur observers with telescopes in backyard observatories log Neptune's position through the seasons. Professional observatories schedule time on their instruments to track the planet's atmospheric changes. The looking continues because each observation adds one more data point to the long record, one more measurement in the continuous project of understanding how Neptune changes over time. Every observation, no matter how modest, is a thread in a larger fabric. The fabric is what science actually is, not the dramatic moments of discovery, but the patient, continuous, often unglamorous accumulation of careful looking by many people over a very long time. One more thread, one more night of looking. It adds up slowly into understanding. Every time something vast is seen from far away, it teaches patience of a particular kind. Not the patience of waiting for something to arrive. The patience of accepting that understanding unfolds on its own schedule, that the picture assembles itself incrementally, that each generation of observers inherits what came before and adds what they can and passes the rest forward. The astronomers of 1846 who confirmed Neptune's existence could not have imagined what would eventually be known about it. The storms, the magnetic field, the diamond rain, the backward moon slowly spiraling inward. They knew they had found a planet. They knew it was far away and blue and large. The rest was questions they did not yet have the instruments to ask. Every era of understanding is like that. Complete enough to work with, incomplete enough to keep working. We are in our own era of that same incompleteness, seeing what our instruments allow, formulating questions our successors will answer, adding our generation's careful looking to the long accumulation that eventually becomes knowledge. The patience is not passive. It is the active, engaged, generous patience of people who care about something larger than what they will personally live to see completed. That kind of patience is its own form of love. Distance does not diminish what a thing is, only what it looks like from far away. Neptune from Earth is a small blue point, barely resolved even by the largest telescopes available to most observers. From that distance, nothing of its interior is visible, nothing of its storms, nothing of its moons or rings, or the extraordinary dynamics that make it one of the most complex worlds in the solar system. And yet none of those things are diminished by the distance. The storms are as large as they are. The winds blow as fast as they blow. Triton orbits as it orbits backward and patient, and slowly spiraling regardless of whether any telescope on Earth can resolve it. Distance changes the view. It does not change the thing. This is worth carrying beyond astronomy into the smaller distances of ordinary life. Things seen from far away, other people's lives, other cultures, other ways of moving through the world, appear simpler, flatter, less detailed than they are up close. The distance compresses them into a point of light, and it is easy to mistake the compressed view for the complete one. Up close, everything is more complex, more layered, more worthy of careful attention than it appeared from a distance. Neptune taught us that. So does everything else, given the chance. Neptune's rings were not always as faint as they are now. The dark organic material that makes up the rings has been processed by radiation over billions of years, cosmic rays and solar ultraviolet light, slowly altering the chemistry of the ring particles, breaking molecular bonds and reforming them into darker, more complex compounds. The rings may once have contained brighter material, lighter ices, that have since been darkened by this long exposure to the radiation environment of the outer solar system. If that is correct, Neptune's rings are not simply old. They are changed by their age, altered by the accumulated effect of billions of years of exposure to forces acting slowly but continuously on the material they are made of. Age is not neutral. It does something to things. It processes them. It darkens some and brightens others, simplifies some structures and complicates others, wears some things smooth and leaves others rough. Neptune's rings carry the evidence of their age in their color, in the organic darkness of the material that composes them, in the slow, continuous change that radiation and time have worked into their chemistry. Old things often look the way they do because of everything that happened to them. That is not damage. That is history. Neptune will continue its orbit long after every human structure on Earth has dissolved. The roads and buildings and bridges that exist right now, the cities and monuments, and all the accumulated physical evidence of human presence on this planet, none of it is built to last on geological timescales. Stone monuments erode. Metal corrodes. Even the most durable human constructions, left without maintenance, return to their component materials within thousands of years. Neptune's orbit is stable for billions of years. Its moons will continue in their paths. Triton will spiral inward over 3.5 billion years and eventually become a ring. The diamond rain, if it falls, will continue falling. The blue atmosphere will continue reflecting the wavelengths of sunlight it does not absorb, sending color outward into space whether or not anything is there to receive it. This is not a melancholy thought. It is simply a true one, and it carries something useful. The universe does not measure significance by duration. A mayfly lives for a day and is fully a mayfly. A human life is brief against geological time and is no less fully a life for that. What a thing is does not depend on how long it lasts. Brief things can be complete. They often are. From Neptune's distance, Earth's brightest cities would appear as nothing at all. The light our civilization produces, the combined glow of every city, every highway, every lit window on the night side of Earth, would be completely invisible from Neptune. The planet itself would be only just visible as a faint bluish point, and the light of human civilization layered on top of that would be swallowed entirely by the distance. There is no irony in this. It is simply what distance does to light. From here, Neptune is a faint smudge requiring a telescope to find. From there, Earth is less than that, a point of light indistinguishable from background stars, without very precise measurement. And yet here we are, on that invisible point, aware of Neptune, thinking about it, spending time in the company of its storms and moons and ancient blue atmosphere, building instruments sensitive enough to resolve its disk, sending spacecraft across the solar system to photograph its rings, naming its features and debating its mysteries and planning future missions to learn more. Awareness travels in only one direction in this conversation. That makes it no less real. Perhaps it makes it more precious. Distance does not diminish what a thing is, only what it looks like from far away. But there is another side to that truth worth turning over gently before the night ends. What something looks like from far away is not always a lesser view. Sometimes distance reveals structure that proximity obscures. Standing inside a forest, you see trees. From above, you see the shape of the forest itself, the way it curves around a hillside, the clearing at its center, the river running along its western edge. Both views are true. Both show something the other cannot. Neptune from Earth is a blue point. From Voyager 2, it was a world of storms and rings and extraordinary complexity. Each distance reveals what it can and conceals what it must. Understanding something fully means finding the right distance for each question. Close enough to see the detail, far enough to see the shape, and patient enough to know that neither view is the complete one, that the thing itself always exceeds what any single perspective can hold. Neptune exceeds what we know of it, as does everything worth paying attention to. Neptune drifts on patient and blue, somewhere in the dark, beyond the reach of unaided eyes. Right now, at this moment, while you rest and breathe and let the quiet of this hour settle around you, Neptune is exactly where the mathematics of its orbit places it, moving along its enormous ellipse at the same unhurried pace it has maintained for 4.5 billion years, carrying its moons and rings and storms and extraordinary interior through the cold outer dark of the solar system. It does not know this night is happening for you. It does not know about the quiet you are in, or the thoughts that have moved through you tonight, or the particular quality of the dark in whatever room or place is holding you right now. Neptune simply continues as it always has, with the patient indifference of something very old and very large that has never needed to know it was being thought about. And yet you thought about it, and that thinking was real. And through it, something connected across 4.5 billion kilometers of space, across the extraordinary improbability of a universe that produced minds capable of reaching outward with curiosity and finding something beautiful at the end of the reach. You reached. It was there. That is enough. That is more than enough. And somewhere in the dark tonight, so do you. You drift in your own way through sleep, through the slow rhythms of a body settling into rest, through the quiet that comes when the day releases its hold, and something older and simpler takes over. The breath slows. The thoughts loosen. The particular urgencies of this particular day begin to feel less particular, less urgent, more like weather that has passed. You are a small, warm thing on a small, warm planet, in a solar system that contains worlds of impossible wind and diamond rain and backward moons and rings made of ancient shadow, and you know about all of it. You spent time with it tonight, and it changed the texture of this hour in some quiet way that will be difficult to name in the morning but will still be there. The universe is not indifferent to being beautiful. It simply does not know that it is. You are the part of it that knows. Let the breath come slowly now. Let the mind release whatever it has been holding, the way Neptune's atmosphere releases a storm, not all at once, not dramatically, but gradually. The edges softening the structure, losing its definition, the whole thing easing back into the blue it came from. Somewhere out there a blue planet is moving through the dark. Its winds are blowing at speeds nothing on Earth could survive. Its moon, Triton, is tracing its slow backward path, patient and ancient, spiraling by the smallest imaginable amount toward a future billions of years away. Its rings are catching faint infrared light and returning it as a warmth too subtle for any human instrument to feel. All of that is happening right now, and you are here quietly in whatever warmth is around you, the weight of a blanket, the soft sound of a room at rest, the particular quality of the dark behind closed eyes. You are made of the same ancient cloud that made Neptune. The same forces that hold its moons in orbit hold you gently against the surface of this planet tonight. The same universe that produced a world of diamond rain and impossible wind also produced the quiet you are moving toward right now. You belong to all of it, every vast and patient and beautiful part of it. Let Neptune drift in its enormous orbit. Let Triton move its slow and ancient spiral. Let the white methane clouds form and dissolve in the upper atmosphere of a blue world 4.5 billion kilometers from where you are resting. You do not need to hold any of it. It holds itself. It has always held itself. And gently in the same way, you are held too by gravity, by warmth, by the simple continuity of a universe that has been keeping things in motion for nearly 14 billion years and has not stopped yet. Rest now. You have traveled far tonight. I hope you sleep well and dream softly. Good night.